Right, we're now going to look at the introduction to the reactor that's called the Continuously Stirred Tank Reactor, or CSTR for short. As the name suggests, the idealization of this reactor is a mixed tank. So what we have is a feed at, say, molar flow rate Na0, which is the moles per time flowing in, and concentration, say, at Ca0, which is the concentration of A flowing in. This flows into a tank, say a volume V, and the contents in this tank are well mixed. The exit stream has, say, a molar flow rate N and concentration Ca. And what we mean by well mixed is that the concentration of the contents of the tank is the same as the concentration inside the tank. So in other words, both this and that are all at the same concentration. That becomes a very, very important point and a big difference between this reactor and the plug flow reactor. A consequence of this is that the reaction all happens at a single concentration, and that is at the exit concentration. And this means the way we model it is quite different to how we handle the plug flow. Let us look how we describe this reactor mathematically. We have a molar flow rate in of Na0 and a molar flow rate out of Na, and the volume of the reactor is V. Remember, what we really do in reactors are basically mole balances, and we now do a mole balance over the tank. What we say is that the number of moles of A entering the reactor, Na0, there we are, plus the moles of A formed in the reactor, which is the volume, and it's the entire contents of the tank, times the rate of the material in that volume, in other words, RAV, and remember that must be the rate at the exit concentration, because that's the concentration of the contents of the tank. So what came in plus was formed must flow out, in other words, must be equal to Na, and there we have Na. We can now rearrange that a little bit, and what we can see is that if we turn that equation around, we can write it in the following form, that minus RAV is equal to the difference in the molar flow rate in and out of the reactor. This equation is important. It is the general equation that describes a CSTR with no assumptions. Now, the next thing we can do is think, how do we simplify this for constant density? Now remember, with constant density, what we have is the molar flow rate is constant. The volumetric flow rate, is constant. So in other words, if we look at the relationship between the molar flow rate, the volumetric flow rate, and the concentration, we get that Na is Q times Ca0. But if we look at the relationship here for the inlet flow rate, the feed, it's Na0, the molar flow rate in, is this volumetric flow rate Q times Ca0. So because it's constant density, the volumetric flow rate here is the same as the volumetric flow rate there. We can then put these terms into this equation and simplify it, and if we do that, what we get is that minus RAV is QCA0 minus QCA, and we can combine these two Q terms with a volume term to get us back to a residence time, and we get that minus rate divided by times V over Q, and remember that term we defined as residence time, which gives us minus RA times tau, that is the symbol for residence time, is equal to the difference between the inlet concentration and the outlet concentration. It is important to remember that that rate must be calculated at the exit concentration.